Today we're looking at the mean value theorem. The mean value theorem gets used in a lot of ways, and it shows up on the AP exam in several different places frequently, and they don't tell you that it's the mean value theorem. You have to know to apply the mean value theorem. And here's what it says. If y's f of x is continuous at every point of some closed interval from a to b, and differentiable at every point in its interior from a to b. So in other words, we don't care if there's a corner or something like that at one of the endpoints. We just care that it's differentiable in between those 2 points. Then there is at least one point in C in the open interval from a to b, so not at either endpoint, at which the derivative at C is equal to f of b minus f of a over b minus a. Remember, what is f of b minus f of a over b minus a? What is that? Slope of what?
F of, wait, the derivative? The slope of the derivative?
No. That's the average rate of change. So graphically, what we have then is if we have a nice differentiable curve, somewhere between points A and B, there'll be a place where the tangent line is parallel to this secant line. I don't normally think about it graphically all that much. I think of it as if you have a nice differentiable function, then someplace between where I start and where I end, the average rate of change will be equal to the instantaneous rate of change. Right? If you have, an average rate of change, let's say that, you're driving someplace and you average 50 miles an hour, it makes sense that at some point, and probably more than that, but at least once, you had to be going 50 miles an hour, right? That's the idea behind the mean value theorem. The mean value theorem is actually one where I suggest to students that they actually memorize it, right? And be able to say, if y equals f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a point C on the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. It's one of the few that I actually have completely and totally memorized. A lot of other things I'm like, I know it well enough, but this one I have it memorized. So first of all, we're going to look at some where the conditions of the mean value theorem aren't met. Now, real quickly here, notice this is an if-then. It doesn't tell you what happens if it's not continuous or it's not differentiable. The conclusion still could happen. What they are telling you is if this hypothesis happens, you have this continuous function on the closed interval and it's differentiable on the open interval, then we know what's going to happen. That someplace the instantaneous rate of change will be equal to the average rate of change. All right, so let's take a look at this one. Explain why each of these fails to satisfy the conditions of the mean value theorem on the specified interval. Well, this first one, I put this one in here because there's never really a time that people teach this, but what is the square root of x squared? I'll give you a hint, it's not x.
Absolute value.
It is the absolute value of x. Because x squared is always a positive quantity, and the square root, it's the principal square root, so it's got to be positive as well. So that's just this absolute value function moved up to, on the interval from -2 to 1, f is continuous. On the closed interval from -2 to 1, but not differentiable on the open interval from -2 to 1, specifically at x is 0. This next one, this is the greatest integer function. Some books write it like this. You'll see it both ways depending on the textbook author. So the problem that we have with this one is that g is not continuous. On the closed interval from 1 to 2. Specifically, at x equals 2, that's where it suddenly takes a jump up, right? Therefore, it's also not differentiable at 2, but we don't care about that. We don't care that that's not differentiable at 2. We just care that it's not continuous. It is differentiable on the open interval between 1 and 2. The slope is always 0. All right, let's take a look at this one. I always check for continuity first, and why do I feel like that's not what I meant for this function to be? Give me a moment. Let me see if I stole this one and just didn't write it down correctly. Well, I don't see it in there. Okay, well, let's check for continuity. So the limit as x approaches 1 from the left of f of x is going to be 1 cubed plus 2, which is 3. But f at 1 is 1 squared plus 1, which is 2. therefore f is not continuous, at x is equal to 1, so the mean value theorem does not apply. Now this next example is one that there's lots of these in textbooks, and the AP will never ask this question. It's real super straightforward. It says, show that the function f of x is equal to 2x cubed satisfies the hypotheses of the mean value theorem on the interval from 0 to 2, and find the value of c guaranteed by the theorem. So, the hypotheses, we have to have a function that is continuous on the closed interval. Well, f is continuous. On the closed interval from 0 to 2 because it's a polynomial. And differentiable on that open interval from 0 to 2. Again, we don't care about differentiability at the end points, just in between. So the mean value theorem applies. So now let's find that average rate of change. The average rate of change is going to be f at 2 minus f at 0 over 2 minus 0. F at 2 is 16, f at 0 is 0 over 2, so that's equal to 8. We'll take the derivative, f prime of x is 6x squared. Then we're going to set those two equal to each other. So 6x squared is equal to 8. Means that x squared is equal to 8/6, which is 4/3. So x would be equal to plus or minus 2 over the square root of 3. But only one of those is in the interval. So c equals 2 over the square root of 3. That's the point on the interval where the instantaneous rate of change equals the average rate of change. Or graphically, the slope of the tangent line at 2 over the square root of 3 will be the same as the slope of the secant line that goes through the points 0, x is 0, and x is 2. So again, just restating that, since f of b minus f of a over b minus a is the average rate of change of f on the closed interval from a to b, and f prime of c is the instantaneous rate of change at c, the mean values theorem says that under the correct conditions, that is, you have to have a continuous function on the closed interval and it has to be differentiable on the open interval, that the instantaneous rate of change at some interior point must be equal to the average rate of change on the entire interval. So, let's take a look at this one. If a car accelerating from a standing start takes 8 seconds to go 352 feet, at some point must the car's velocity have been 44 feet per second? Well, the average rate of change in the position which is the same thing as saying the average velocity, is going to be equal to, well, it went 352 feet in 8 seconds. Which is 44 feet per second. So, since the position function is continuous and differentiable, therefore, by the mean value theorem, the car's instantaneous velocity must have been 44 feet per second at least once. Sometimes when you're doing a lot of mean value theorem problems, because so often it just happens once, people tend to forget that it could happen multiple times. Okay, any questions about that? All right, you have the worksheet, because I actually remembered to give you the worksheet this time.